All right, my friends, it says to use the integral test, but first let's just kind of do our little checklist as to whether this problem qualifies. So, let's think about y equals e to the negative x, right? So think graphically about y equals e to the negative x. If you were to graph it, it looks something like this. Is it always above the x-axis? Check. Is it continuous everywhere, at least from 1 to infinity? Check. And is it continuously decreasing for all the way from 1 to infinity? Check. So if you can say those three things about the function that you're dealing with, then you can proceed and use the integral test. Okay. So let's get started. The first thing we're going to do is we are going to consider the related integral. Okay. So we're going to say some transitional word to kind of get started. So we'll say something like, notice that. You do want to learn how to be able to kind of write and have words around your math. Anyway, so notice that the integral from 1 to infinity of e to the negative x dx, which is equal to the limit as b approaches infinity of the integral from 1 to b of e to the negative x dx, which in turn is equal to the limit as b approaches infinity of the opposite of e to the negative x from 1 to b. Let's plug the bounds in. We'd have the limit as b approaches infinity of the opposite of, I'm going to write, when I plug b in, I'm going to write it like this. For me, it makes it a little more obvious. And then we'd be subtracting a negative. So we'd be adding, let's see, when you plug 1 in, you'd get 1 over e. Okay, now let's let the remaining b approach infinity, and notice that this fraction would approach 0. And so we ended up with 1 over e, which is finite. And so we would know that the integral converges. So we would then know the integral from 1 to infinity, e to the negative x dx, that it converges. And by the integral test, the sum as n goes from 1 to infinity of e to the negative n also converges. Okay, so if you came to the same conclusion, then that's great. If using this type of wording for your explanation makes your argument more clear, then I would definitely encourage you to borrow that, okay? You're going to need to have this language kind of in your back pocket and ready and practiced when you get to the AP exam. So I really recommend as you go through the problem set, go through the notes and the problem set, that you don't just give outlines of your answers, that you actually practice writing fluid sentences with math in between. Really, that's getting ready for the AP exam, way more than just getting the answer in the back of the book. I hope that makes sense. Okay, the number one thing that a lot of folks don't like about Part B is that it wasn't given in sigma notation. So if something wasn't given in sigma notation, you can always put it back in sigma notation. And this one, it actually gave you the rule for how they're generating the terms. But if they didn't give you the rule, typically you could have figured it out yourself, just doing, stuff that we've been doing all along anyway. So definitely that's the way they're generating the terms. And then they would have started at 1. How do I know? Because if I plug 1 in to this rule, I get, the first term, and then going to infinity like so, and, is this always going to be positive, at least for n starting at 1 and going to infinity? Yes. Hopefully that makes sense. Is it, continuous? Yes, you could set that denominator equal to 0, but you wouldn't get a real result. So it's continuous. And is it decreasing in value? It is, because the expression on the bottom is getting bigger way faster than the one on the top. You could also use calculus and show that the derivative of the way they're defining the terms is always negative. That's another way to do it. So anyway, so it fits the three conditions. And so now we can kind of move to looking at the related integral. So let's notice that the integral from 1 to infinity of x over x squared plus 3 with respect to x, let's go ahead and figure out what this would be. So first, let's fix the notation. Limit as b approaches infinity of 1 to b, x over x squared plus 3 with respect to x. To do this one, I would probably let u equal x squared plus 3. Our du would equal 2x dx. And so writing this in terms of u, we would have the limit as b approaches infinity of 1/2. I'm going to change the bounds in a second. So first I'm going to go ahead and just say 1 over u du. And now I'm going to change the bounds. So if x is 1, my friends, if you plug that in right there for x, then your new u value would be 4. And if x was b, then your new u value would be b squared plus 3. Okay, so then we would have the limit as b approaches infinity of 1/2 times the natural log of the absolute value of u as u goes from 4 to b squared plus 3, which would leave us with the limit as b approaches infinity of 1/2 times the natural log of, absolute value marks are unnecessary for something like b squared plus 3. And then the absolute value marks are also unnecessary for the 4. Okay, so let's let the remaining b approach infinity. So b squared would approach infinity, adding 3 would approach infinity. Take natural log of infinity, you get a slow growth infinity, but you do get infinity. So this entire expression would approach infinity. So we'd be left with 1/2 times the quantity, basically big ol' infinity, take away natural log of 4. I suppose I should say approaches, not equals. Since by definition of infinity, you can never quite equal infinity. Anyway, infinity take away natural log of 4 would be infinity, and half of infinity, still infinity. Okay, so what do we know at this point? We would know that the integral from 1 to infinity of x over x squared plus 3 dx diverges. And by the integral test, what would we know? We would know the related sum also diverges. There we go. All right, my friends, again, the little English sentence stuff around the math is going to be pretty important to practice. You don't want to get close to the AP exam and be practicing that for the first time. All right, my friends, let's take a look. Actually, you know what? Before we take a look at example 2, let's talk about a shortcut. And we are almost, I think we're almost done with this lesson, to be honest with you. This one is a little bit on the shorter side. Yeah, we are almost done here. Okay, so before we do example 2, let's talk about a shortcut that we could have used for the warm-up. Let's talk about recall. It's been a while, but from section 7.5, there was a special type of integral. And so let's talk about that. There was the integral, and if it was from 1 to infinity of 1 over x to the p, where p was a constant with respect to x. So basically, we found out that based on the p-values, you could actually just tell by looking at it that there are certain p-values that would make this thing diverge. We'll fill this in a second. And then there were certain p-values that would make this thing converge. And so if you remember, converging means adding up to something finite. And so you'd want to have a p-value that would make this, if you want it to converge, you'd have to have a p-value that would make this approach 0 really fast, so that even though you're adding up infinitely many terms, you could get something finite. And so let's think about that. I remember the threshold was 1. That was what made things converge or diverge. And so we'll actually find that this series will diverge for p-values that are less than or equal to 1. So think about some examples like if p was 0, that's less than 1, then you'd have 1 over x to the 0, which would be 1 over 1. So you'd have this like horizontal line. So of course that would, have an infinite amount of area. Anyway, and then it would converge for p-values that are anything greater than 1, even like 1.1 or something like that. So, so that recall that. And then if you take that and mix it, add in the concept of the day, the integral test. If you add these two concepts together, you get what's called the p-series test. And so let's talk about what the p-series test is. The p-series test says if you have a sum as n goes from 1 to infinity of 1 over n to the p, well, then you could tell by looking at the p-value whether it's going to converge or diverge. It will converge for and diverge for which p-values? Well, take a wild guess. So any graph like that would fit all the things that, all the conditions you'd need to apply the integral test. And so the integral and the sum will do the same thing. So if your p-value is less than or equal to 1, you've got something, oops, I have this backwards. I wrote the wrong word, sorry. Diverge. Sorry. Converge. There we go. Okay, it will diverge for the same p-values that made the other one diverge. There we go. And it will converge for the same p-values that made the other one converge. There we go. Okay. I hope that you have been memorizing these tests as we go. It will be very necessary for your success. But this, my friends, is probably your best friend when it comes to chapter 8, or one of your best friends, because it's easy and we like easy. Anyway, so it's something that you'll find useful even as we go into future stuff. So, all right. So using the p-series test, see if you can make light work of example 2, which asks you to determine, sorry about that, to determine whether each series converges or diverges.